So let's start our one-to-one talk series. That's the third episode we are talking about. The topic today would be bivariate distribution. Since we are a bit late, we cannot finish the complete thing today. So we'll just start with a few theoretical aspects and then we'll go to a few problem-solving strategies. But let's start with the very basic concept of bivariate data. First, you need to learn about bivariate data in order to delve deeper into the bivariate distributional concept. So first learn what is bivariate data. That's a very basic thing, because I think you people have already learned univariate data, like height univariate data. But when height and weight comes together, you get a bivariate data. In this way, we can extend the concept up to a multivariate data, the highest form of statistical distribution, the multi-dimensional data set. Anyway, so the basic concept of bivariate is literally required in order to get a hold of the multivariate data. And in multivariate data, you have to learn various aspects, which is essential in machine learning, in model building, etc. So as a foundation, bivariate data analysis as well as bivariate distribution is a very, very important topic. Okay, so let's clarify a few very common mistakes and all. So let's start with the concept of just a second. Yeah. Okay, so let's begin the concept from bivariate random vector. You have two random variables moving simultaneously. It's called a bivariate random vector. So the very first concept starts from a bivariate distribution function. Denote the bivariate distribution function by fxy xy. This is nothing but probability capital X less than equals to small x intersection capital Y less than equal to small y. Just try to distinguish between the univariate setup and the bivariate setup. The univariate distribution function stands for one single fxx, which is nothing but probability capital X less than equals to small x. Now in bivariate setup, you have one more random variable to handle, which is capital Y here, and the two random variables are moving simultaneously. X is less than equals to x, and simultaneously capital Y is less than equals to y. So we are essentially computing this joint probability. For this reason, the bivariate distribution is also called the joint distribution. Okay. So that's the very first concept, that bivariate distribution function. Okay. Then the next concept, bivariate PMF or bivariate probability mass function. Or sometimes you can call this as joint probability mass function. Now, what is meant by bivariate PMF or joint PMF? Let's recall the univariate PMF once. Suppose X is a random variable. The PMF of X is fxx, which is a probability that the random variable capital X is taking the value small x. Okay, that's a very basic idea of PMF. PMF is essentially a probability quantity with some other properties like every value has to be more than equal to 0. And if we sum the PMF over all the values of X inside the support, it will be 1. Now, what is meant by support? Support means the set in which the random variable X is defined. It's called the support. Okay. Now, let's move on to bivariate PMF or joint PMF. So what is the idea? Let's denote this by fxy xy. Once again, almost same as the univariate case, just you have to define probability. X should take the value small x and y would take the value small y simultaneously with x. So that's the one catch you have to maintain throughout in your bivariate distribution study, that x and y would hold each other's hand and move simultaneously. That's why it is called a bivariate probability. Two variables are here. Okay. So this is the idea of bivariate PMF or joint PMF. Now, to be more formal, let's become more formal. If this is bivariate joint PMF or joint PMF, then this function would be more than equal to 0 for every xy belonging to S. Now, in bivariate setup, what is S? S is called the joint support. Okay. Now, what is meant by joint support? That's a very interesting and tricky question at the same time, because in bivariate problems, the most problem we face in this joint support. Okay, sometimes the range are very tricky. I guess in some other session we can discuss about some tricky range. Most ISI problems are like this. A few jam problems are also like this. Okay. Anyways, we'll discuss about that tricky range later on. But now, bivariate PMF, the function always takes non-negative values, and if we sum, here the sum would be a double sum over x and y, then the sum would become 1. Now, the interesting part would be how to determine the range of the sum. Together, x and y would belong inside the support, but in practice, how the range can be set. Okay, very simple idea. One range you have to keep free, and the other range you have to make it dependent. Okay, that's the catch, that's the idea. For example, suppose x is ranging between 0, 1 to up to n. Y is ranging in between 0, 1 to up to n. And x plus y, this is less than equal to n. For example, I'm just giving you a demo example, how to determine this summation. Okay. If you keep the range of x a free range, then x would move in between 0 to n. But then you have to keep the range of y as a dependent range. So y here is less than equals to n minus x. Y is starting from 0. So in the summation, y would start from 0 and it will move up to n minus x. Then just you put up your joint PMF and the value would be perfectly as 1. Okay, so that's the trick you have to maintain always. Now you may ask, can we just interchange the range? Yeah, you can, surely, but depending upon the situation. Okay, so if you want to interchange, then definitely you can move like this. Make the range of y free. That is, y would move in between 0 to up to n. But you have to make the range of x dependent. So x would be less than equals to n minus y. So x would be 0 to up to n minus y, and y would move in between 0 to n. The same thing will happen. The result would just be the same. Okay. So that's the idea of joint PMF. Now, quite obvious, when we are talking about joint PMF, then we mean that this bivariate random vector, why we are calling it vector? Because it's a two-dimensional random variable. That's why sometimes I refer bivariate random variable as bivariate random vector. Okay. Now, since we are talking about mass function, then definitely the corresponding bivariate random vector is discrete in nature. Okay. Now let's talk about bivariate joint PDF. What is meant by bivariate joint PDF? Let's denote this as fxy. I guess you people know that PDF is not a probability. Although it is called probability density function, but PDF is not a probability. Categorically speaking, I repeat, PDF is not a probability, but PMF is definitely a probability quantity. Be very careful to these terms and these ideas. They are the basic one. Okay. So anyway, so bivariate joint PDF is not a probability quantity. Now, how to define a joint PDF? Very simple. If the function satisfies this two quality, number one, the function would be non-negative for every xy belonging inside the support. That's part A. And in part B, if we double integrate this joint PDF over x and y, then the answer would be 1. Once again, you have to put up this range in a careful manner. You have to be very, very careful. Okay. XY, the range XY belongs to the support. Now, in reality, in practice, how to put up this range? Let's give me an example. Suppose you have a joint support like this. Okay. Joint support means tentative all possible values of x and y. So the trouble is here, just imagine there is no y. Just imagine for a while. then range of X would be 0 to 1. Imagine there is no X, then range of Y would be 0 to 1. This range is called the free range of X, and this range is called the free range of Y. That's one aspect. In other aspect, we see a dependence here. How? X lies in between 0 to Y. So this is the dependent range of X. Okay. And we see clearly Y lies in between X to 1. So this is the dependent range of Y. So one range of X is completely free of any other random variable which lies in between 0 to 1. One range of Y is free from any other random variable which lies in between 0 to 1. And in other sense, X depends upon Y like this. X lies in between 0 to Y and Y lies in between X to 1. These ranges are called the dependent ranges. Okay. Now, I was talking about how to put up the range of X and Y. Let's see. Inside you have your joint PDF. Now, if you put the dependent range of X like this, then you have to put the free range of Y like this. The answer would be 1 because you are integrating the joint PDF. The answer would be 1. Okay. Now, the converse. If you are putting up the dependent range of Y, that is X to 1, then you have to put up the free range of X like 0 to 1. The answer would just be the same. But when to use which range, it entirely depends upon the problem. Okay. This is just a toy example. We can have several situations where the range would be different. So we have to first detect the proper ranges. First of all, we need to detect the free range of X and free range of Y. Then we need to detect the dependent range of X and the dependent range of Y. That's a very, very primal idea of bivariate probability distribution. Okay, this idea is highly required in any problem solving strategy. Okay, so that's the idea of joint probability mass function and joint probability density function. These are the primary ideas. Okay, now let's move on to another concept of independence. Independence of bivariate random vector. If X and Y are independent, then their joint probability function, be it the joint PDF or be it the joint PMF, it can be written as a product of their marginal PMF or PDF. Now the question is, what is meant by marginal distribution? This is the joint PMF, say. If X and Y are independent, then the joint PMF can be written as a product of, that's the marginal PMF and this is the marginal PMF of Y. Now that's a very, very important term, marginal. I'm coming to that point. Just wait. If this is a joint CDF, then under independence, the joint CDF can be written like this. The marginal CDF of X multiplied by the marginal CDF of Y. Now, the fundamental zone, what is meant by marginal distribution? That's a pretty important zone in bivariate analysis. Okay, so you had the joint distribution of X and Y. But now I want to know the individual behavior of X and Y. That individual behavior is called the marginal. For example, you have information about two persons A and B. Okay. But you have all the joint information. Okay. For example, you know that B goes to sleep exactly 2 hours after A goes to sleep. This information is a joint information actually. Okay. You know how the sleep of B is dependent upon sleep of A. But now you want to know what is the exact sleeping time of B irrespective of sleeping time of A. That's the marginal information you now need. Okay. In bivariate analysis, we have all the information regarding the joint movement of X and Y. I know their joint CDF, I know their joint PMF, everything I know. But now I want to know the individual behavior of the random variable capital X. This individual behavior is termed as the marginal distribution. Okay. So how to get marginal? Let's see. Marginal PMF of X. How to get this? If XX is the marginal PMF of X, just I will sum the joint PMF over Y. That's all. And you will get the marginal PMF. But the fundamental question is, which range of Y I need to put here? Definitely you need to put the dependent range. Okay. The resultant answer is the marginal PMF of X. Now, how to get the marginal PMF of Y? just sum the joint PMF over the range of X. Once again, the fundamental question, which range to be put here? The dependent range, of course. Okay. Now, marginal PDF, how to get them? The marginal PDF of X, I can get it by integrating the joint PDF over Y. Which range to be put? The dependent range of Y. At last, the marginal PDF of Y. How to get this? Integrate the joint PDF over X over X, the range. Which range? The dependent range. Okay. Now let me tell you a fun fact. In some problems, the life becomes too easy. For example, in this problem, the joint support is like this. 0 less than X less than 1. 0 less than Y less than 2. Here the fun fact is, no range is dependent here. All the ranges are free. Okay. So dependent range, independent range, both are 0 to 1. Dependent range, independent range, both are 0 to 2. But in some problem, you'll be facing hardcore challenges. Okay, for example, this, maybe in some problem, the support is like this, xy, such that mod x plus mod y less than 1. Now, how to detect the dependent range and the independent range? Modulus quantity. So more than 0. Mod x and mod y both are more than 0. Okay. Right? The sum of two positive quantity is less than 1. Then individually, mod x has to be less than 1. Hence, the range of x is -1 to +1. And individually, mod y needs to be less than 1. So that's the idea. They are the free range of x and y. Now, how to get the dependent range? Mod x less than 1 minus mod y. This is the dependent range. So x lies in between -1 minus mod y to 1 minus mod y. Similarly, mod y is less than 1 minus mod x. So y lies in between -1 minus mod x to +1 minus mod x. Maybe there can be more complications inside this. I'm not delving deeper. I'll go there while I'm solving some problem. Bivariate problem can really be very clumsy at times. Okay. The range is really a tricky thing in the whole bivariate analysis. Okay. Now, let's move on to the next concept called the conditional distribution. What is meant by conditional distribution? The conditional distribution of x given y equals to some value small y is defined as f of, in the above you have the joint PMF or PDF, and below you have the marginal PDF or PMF of y. Now, what is meant by conditional distribution? Essentially, by conditional distribution, we are getting the distribution of x, but not the exactly the free distribution of x or the marginal distribution of x. Here, we are getting the distribution of x subject to the restriction that another random variable capital Y would be fixed at some value, small y maybe, or small c maybe, or 10 maybe. So we are detecting the distribution of x given that capital Y is fixed at some finite value. Okay, how to get this? The idea comes from the conditional probability, which has a formula like this: probability A given B. This is probability A intersection B divided by probability of B. This is the very basic definition of conditional probability. This definition of conditional distribution comes exactly from the idea of conditional probability. How? Treat this as the event A and this as event B, and think in a fictitious way that you want to calculate probability A given B. Then in above you have probability A intersection B. That is, x and y would move simultaneously, that is intersection B. And in below, you have only P of B, that is only y would be there. Only y stands for the marginal. And the simultaneous movement of x and y stands for the joint. So the ratio of joint to the marginal is actually called the conditional distribution. This idea is essentially evolved from this conditional probability concept. That's it. So in similar way, how we can get the conditional distribution of y given x? The conditional distribution of y given x equals to some value x. Similarly, in the above, you have the joint PMF or PDF, whatever. And below you have the individual distribution of x, that is the marginal distribution of x. Now, a few days back, there was some debate about x given y. It's an incorrect statement. Yeah, partially true, because there is nothing called x given y. Always x given y at some value. But notationally, if I say x given y, then by default we are saying that y is being fixed at some value. That's why I'm using this particular word given. Given means we are given the value. Otherwise, I would have not used the word given here. It's trivial. Okay. Sometimes people love to make non-trivial stuff to trivial, and in the converse, trivial stuff to some non-trivial stuff. Anyways, that's human nature. Anyways, so x given y, that means x is given at some value. Y given x, this means x is fixed at some value. Okay, so let's move on to the next item. The next item is bivariate moment. Okay, or bivariate expectation, you may say. You have a function of x and y, psi xy, and you need to calculate expectation of psi xy. How to calculate this? You are given that the joint PDF of x and y is fxy xy. The very basic formula is just put up double integral over x over y, put up this function psi xy multiplied by the joint PDF fxy, then dy dx. Now once again, that same argument, how to put up the range, the same logic. One range has to be the free range. Maybe here you are putting up the range of y as the dependent range, and essentially then the range of x you have to put up in a free manner. In the next session, we'll be discussing problem. There I can illustrate this in a more vivid and clear manner. Okay. Please let me know in the comment box which problems you want to discuss with me. Okay. Anyways, expectation of psi xy, this is double integral psi xy multiplied by the joint PDF dy dx. If x and y are discrete, then expectation of psi xy, this is the joint double summation psi xy multiplied by the joint PMF. Once again, the same saga with the range. One range you have to make dependent one, and the other range you have to make it free. Maybe x has the free range and y has the dependent range. Now, naturally, some question may pop up to your mind. Which range to make it free and which range to make it dependent? It will entirely depend upon the problem. As we will be solving the problem in the next session, I'll discuss this thing in a more vivid and clear manner. Okay. Okay. So the idea of bivariate functions expectation is somewhat like that. Now, what is a moment? This is called bivariate raw moment, okay, of order Rs. Mu prime Rs, we can denote like this. Okay. The formula would be, you may treat x to the power r, y to the power s as your psi xy function, surely. So mu prime Rs would be once again a double integral x to the power r, y to the power s multiplied by the joint PMF dy dx, put up the range of y, put up the range of x, make someone free and make someone dependent depending upon the situation. and you will get the bivariate moment or the joint moment or mu prime rs, whatever you call it. Okay. Now, let's have a glimpse into the idea of bivariate moment generating function. Bivariate MGF. What is that? Bivariate MGF is defined as expectation of e to the power t1x plus t2y. In univariate case, this is the expression for MGF, expectation of e to the power tx. In bivariate case, the MGF is defined as like this, expectation e to the power t1x plus t2y. Once again, you may treat this function as psi xy, and the formula would just be the same, double integral e to the power tx plus t2y multiplied by the joint PDF dy dx, range of y, range of x, make one range dependent, make the other range free, and bang on. Simple. So in the next class, in the next session, this one-to-one live session, that will be on Friday once again maybe, or Saturday, I'll say to it, we'll start solving problems. We have learned a lot of theories. Next will be start solving problem, and we'll learn a very important thing called conditional expectation. Okay, and a few formulas like this. Expectation of y is expectation of y given x. Once again, some people may say, why I'm not writing x equal to small x here? I'm not writing because I don't want to write. Okay, that's my choice. This expectation of y given x, this is called the conditional expectation. Of y given x at some value for sure. Given x means x is being fixed at some finite quantity. This is a very important concept. Many things you have to understand regarding this. We'll continue this lecture session in the next class, maybe Friday or Saturday. Stay blessed and keep solving.